So, in this lecture, we are going to try to show this result by simulation. So, suppose I say I do not give you any mathematics, I ask you to go and say, okay, can I do this whole central limit theorem by simulations? That is what I want to do today. So, now the most general central limit theorem can also be verified by simulation. That I will leave as exercise. We will do a special case today. So, we will do a special case. But the technique is available for everybody. The technique can be used for everybody. The technique can be used for all distributions. It's for about. Okay, very good. So, what I will do is I will not show the general central limit theorem, which says that root n x n bar minus mu by sigma converges to normal 0 1. I will do the binomial case that we did before. That is, I will take sorry about that. What's going on? How do I go next line? So, what I will do is I will take each xi as distributed as Bernoulli p random variables, then Sn is binomial np random variable, which you have checked before. Then we want to check for what p does this statistic Sn minus np by root np times n 1 minus p is close to normal distribution. So, just recall the central limit theorem says actually that probability that Sn minus np by root np times 1 minus p less than equal to x, this converges in as n goes to infinity to minus infinity to x e to the minus y squared by 2 over root 2 pi. That is what central limit theorem says, right. So, what we are going to do today is we are going to check, we are going to simulate this statistic. So, we are going to simulate this statistic, we will simulate statistic, and then we will simulate Sn for various p and n. That is one thing we will do, and then we will check how do the histograms converge. Do the histograms look like normal of the data set? Does it look like normal? That is what we will check. Okay. Very good. So, how does one do this? So, how does one go and perform this exercise? So, let us go and let me just go to RStudio that we have installed. So, I have already prepared a code there. So, but I will just go through it line by line, little slowly, so we can all go through it line by line. So, first thing is I have done here is I have made. Let me make it a little bigger so you all can see it perhaps on the slide. Yeah, very good. This is quite big. So, now let me close this side so the whole studio comes quite really very nice. So, now the first thing I am doing is in this line I am just generating using the rbinom command. I am generating 100 samples of binomial 10 comma 0.25. That is just the rbinom command. So, it just generates 100 samples of binomial 10 comma 0.25 random variables, right. So, now let us say I run this, okay, I can do that way, or I can do what I can do, I can use the replicate command. It is also quite useful. In this I use rbinom, I generate one sample of 10 comma 0.1 and I repeat the command 100 times. So, that is also doing the same thing, it generates 100 samples of binomial 0.1. The last one generates 100 samples of 10 comma 0.5. So, I have generated 3 things, binomial 10 comma 0.25, binomial 10 comma 0.1 and 10 comma 0.5. So, those are 3 things I am going. Okay, let me go back to the slide here. So, what I am doing here is that, I'll take p n equal to 10, I'll take p equal to 0.1, n equal to 10, p equal to 0.5 and n equal to 10 and p equal to 0.25. These are 3 things I am generating. I am going to generate 100 samples of each, right. So, this binomial generate 100 samples of these. So, generate 100 samples of this of binomial n comma p for this p. That is what I am going to do. Right. So, let me mark that in red in a square. So, that is what I am going to do, and then that is what simulation is about. And then the next thing I'll do is I'll go draw the histogram for this, right? Let's go to the histogram. Let's go. So the first thing I do is I generated these are now all these samples are there. You can just check, for example, you can just type binomial sim1. It'll give you all the samples that you have. So I made a mistake in spelling. I'm sorry about that. Binomial sim1. It should give you all the samples generated. It's like 4, 1, blah blah. Okay, that's 100 samples generated. So now what I'll do, the first thing I'll do is I'll go plot the histogram. So first thing I create a space. So what I do its graphical entry parameters. 1, 3 ensures there's 1 row and 3 columns. So let me run that. That's part I want. Then let me do histogram first. So here's histogram of binomial 10, 0.25. So you can see it's skewed to the right in some sense. So it's like, so everybody is sort of has a long tail to the right, but everybody is on the left hand side. So 10, 0.25 means the mean is around 2.5. So somewhere here is the mean, and then that's where everybody is. That's very nice. Then let's plot 10, 0.1. That's what I'm doing next. So we do that. Then what happens? Then it's even more skewed to the left because, like, there's nobody after 4. Here some people after 6 and so on. It's very, very asymmetrical. So it's not quite there. It doesn't look like normal as yet. Then then let's run binomial 10, 0.5, and lo and behold we find that's quite symmetrical. Very nice. So 10, 0.5 is kind of symmetrical, and this you could think, okay, it is like a shifted normal in some sense. The mean is around 10 times 0.5 is around 5, and the variance is around quite reasonably defined. So the plot it seems that symmetry is achieved for n equal to 10 and when p is equal to 0.5, not p to 0.25 and 0.1. So let me just go back to the slide. I'll summarize this. I'll just go back to the next slide. Let me go down. So here I've done these commands. In the first one I did 100 directly from R binom. The second one is a replicate command. I chose one sample and I repeated the command 100 times, and same thing for 0.25. So then I found out in this simulation that that the 0.1 and the 0.25 are not quite symmetrical, but the 0.1 and 0.25 are not symmetrical, but 0.5 is kind of symmetrical. So symmetry is achieved. So at n equal to 10 and p equal to 0.5, but not at p equal to 0.1 and p equal to 0.25. Very good. So now let me standardize this. Let me go to the thing. Let me standardize this. So how do I visualize this? So the way you visualize it, you standardize it. So what you do is you have to take the bounded random variable, subtract the mean, and divide by the variance, square root of the variance. Right? That's what standardizing is. Let me go back here. So what does standardizing mean? You take a random variable here. Here what you do is you take a binomial random variable. So let's call this as let's call the random variable as y. Let's say y is binomial np, where n and p are appropriately in this let's say I should use s, I guess. Let me use s. Sn, let's say Sn is binomial np. So here what I've done is I've standardized it. So what standardized means what? I've taken Sn minus n is 10. So let's say n is 10. Let me just rewrite it. Let me erase it. So in this thing what I've done is I've just taken the previous histogram data set that I have. I've taken S10 minus 10 times 0.1, that's 1, divided by square root of 10 times 0.1 times 1 minus 0.1, that's 0.9. That's what this guy is doing. What's happening here? Here I'm doing S10, n is 10, but p is 0.25, so it's 2.5, right? 10 times 2 is 2.5. The whole thing divided by square root of 10 times 0.25 times 0.75. That's p. And here what I'm plotting, I'm doing S10 minus 10 times 0.5 is 5. The whole thing divided by square root of 10 times 0.5 times 0.5. That's the plot I'm doing, right? Again, we see that, okay, if I standardize it, somehow it's still not sort of 10 is not large enough somehow to see central limit theorem. Somehow this doesn't definitely the first two don't look like normal. Second looks kind of normal. The third is a little bit away in that sense. So let me go back now to the R. Let's see how the R does. So I do the same thing. I run this command. I create standardize one, standardize one, standardize one, and let me plot again. Let's see how it looks like now. So let me clean this plot. Very good. So let me go and clear this plotting area again. Let me plot it again. Let me plot the first one. That is 0.1. Let's see how it looks like. So 0.1 doesn't look at all like normal. It's sort of standardized one. Third one, second one, it's getting there. The mean is 0 now, but still it's sort of not so symmetrical. And then 0.5, that's not so bad. I mean, it's still not quite does the job, but it is kind of getting closer and closer to normal in some sense. But you don't. but the key thing is that 10 is not large enough. Okay. So what one could do is one could say, okay, fine, if 10 is not large enough, can we do 20 and see what happens, right? So 20 and see. So 20 in this simulation looks like this. Let me go back to the code that I have here. So again, I do 20. I replace the previous code by 20, and this is like n equal to 20. The same thing. I replicate the binomial sample. Let me make this a little bit clear here. Let me go back here. So you can read in one line. So that's right. So I do the same thing. I divide by the variance. Right. So let me go same thing. Let me sim 1, 20, and then this one. Right. Now let's say I plot it. Let me clean the plot space. Let me start again. Let me create the structure. Let me plot 20. That's not so bad. 0.1, 0.25 is not so bad again, and then 0.5 is quite nice. It looks very nice like normal. So 20 seems to be much better. So 20 seems much. So in the same thing like in this thing, 20 seems much better. Right? So all I did was I just took S20 minus same thing 20 times 0.1 divided by square root 20. I leave this code on the course website. In my website, you can take a look at this code. The third one, I can go here and I can do the same thing. I run again. I do 50 now, n equal to 50 now. Let's try n equal to 50. Let's see how it looks. So n equal to 50, we're getting closer and closer to normal for all three. So right, so if you do many times, so 50, you do this, come here, you do this, come here, come here. Let me clean the plots again. I run the plot, histogram. I do this one, I get very close to normal, not bad. The second one is okay, and the third one is very, very good. Let's look at it, very close to normal. Of course, there's a little peak here, sort of a little misnomer, but it's kind of getting close to normal. So n equal to 50, we are kind of close to normal 0, 1 in most cases in this case. So the one thumb rule for generating normal random variables or getting close to normal random variables from binomial is the following. You should have this particular rule, that if n times p should be at least 5 and n times 1 minus p should also be at least 5. Then the binomial will be close to normal distribution. Okay. That's the punchline. That's the thumb rule one can keep to do this. And this is one way of verifying by simulation. You simulate samples first, look at the histogram, and then check if the histogram matches the normal distribution. Okay. So just to quickly recall, we start off with this first slide. Let me go back up. So start off with the idea that how do I verify this, and I said that to verify this one has to sort of go and verify, look at the histograms of the standardized binomial distribution, that is Sn minus Np by root Np times 1 minus p. You simulate Sn for various p and n. I did it for 10 equal to 10 and p in these three ranges, so the left symmetric and right symmetric and so on and so forth. Left skewed, right skewed and symmetric and so on and so forth. So then you do this command using either the rbinom command or the replicate command, and then you find that you're doing not so good with 10, you're doing much better, a little bit better with 20, and you're doing very, very well with 50. That's the idea. And the thumb rule is that if np is at least 5 and n times p is at least 1.5, then you're okay. But actually, if p is close to 0.5, you're always okay. Otherwise, you use this rule that np is and n times 1 minus p is 5. Okay, thank you.